Okay. It was working in the first place. John, give me the half reactions. Iron solid. He's going to Fe plus 2. And then plus 2E minuses. Okay. How about somebody else? Jeff, give me the other half reaction. The copper 2 going to copper solid. And we're not quite balanced. You have to add the 2 electrons to the copper 2. Otherwise it won't. And then you could add these guys up, and you get the exact same thing we had before, which is how it's supposed to work. Okay. What is the standard electrochemical cell potential for this reaction? Okay, now how are you supposed to figure this out, Adriana? Standard electrochemical cell potential. Yeah. Okay. So the iron, here's one of them. Iron solid. Now we have Fe solid going to Fe plus 2. So what's my E0 for that? Positive. You had to flip the sign, right? Okay, and then everybody, how about find that copper one? Copper plus 2 going to copper solid. 0.15, positive. Okay, so my E0 will be what is that, 0.59? Okay, that is my E0 cell. Oh, sorry, that's this answer down here, right? Write the line diagram. Okay, for a voltaic cell that utilizes this redox reaction to do useful work. Now, for it to do useful work, you can't have all the stuff in the same beaker. All you're going to get is just iron dissolving, right? It's like shorting your battery out. You're not getting any work done. So you have to run it through something. You have to separate those guys out with a, what is it called? Salt bridge. Yeah. So you're going to have the iron half reaction in one beaker, the copper in the other, and a little wire connecting the 2 electrodes. You use a light bulb or a voltmeter or something. Okay. And then all I do when I'm messing with this, if you look at the half reactions, technically what's supposed to be on the left-hand side? Does anybody know? Is it the oxidation or the reduction? The oh, sorry. It's so hard when I face this way and go look at this thing. What's supposed to be over here? I thought it was oxidation. I thought it was oxidation going on here. I'm pretty sure it is, because they want the electrons to be flowing from this cell to this cell. So they want oxidation going on over here. So pretty much all you do is, if you have this written out, it's so much easier. You write Fe solid. You just write the stuff, write the reactants, write essentially what's in that half reaction out. And you can put commas and things, but the correct convention is if there's a phase change, like solid to aqueous, you're supposed to put a line. Okay? And if they would have told us the concentration of that iron 2, you would have put it right in here, right in front of it. But they didn't, so you just leave it alone. And then you have the salt bridge, and then you have to do the same thing for the other side. So it would be Cu plus 2. If you know its concentration, you'd write it. And I draw a line because it's a solid. Which one's the anode, which one's the cathode? Anode, the only way I remember this is both anode and oxidation start with a vowel. It's the only way I've remembered this for 20 years. So the anode is going to be which side? Yeah, the iron. He's producing the electrons, right? Oxidation. Anode is where oxidation occurs. Fe solid going to Fe plus 2. So they always want the anode over here to produce the electrons, so electrons flow from left to right. That's their convention. It's kind of a nice convention, because if Amanda does the same thing over in Europe, and she just has these things flipped around, like the plus and the minus flipped around, she gets the exact same result, but it's off by a what sign? a negative sign, right? If you're reading positive numbers, she's reading negative numbers. So this way, just always have oxidation over here, and then everyone will agree. Yes?
So when you draw it, like the actual drawing, like it said in our homework, the oxidation flows to the negative side of the volt meter?
You should have, I don't remember the,
Because like in the book, that's how all of them were drawn. Like it was like negative to positive, and then total.
oh, that is, it is, this is kind of, this would be your negative terminal,
Okay.
because he is producing the electrons. He's your positive terminal, because he's reacting with electrons. So that's true. This is kind of your negative and your positive terminal. I didn't really think of it that way, but that's true. It's a battery. It makes sense. Electrochemical battery. Okay. Non-standard conditions. What does it mean, Pablo, to be under non-standard conditions? Good. No, not 25 degrees Celsius. And what else? 1 atm for gases. And what else? 1 molar for aqueous, any solutions. They're not 1 molar. Change any of those guys, and you're under non-standard conditions. Right. So under non-standard conditions, notice that the little superscript 0 is gone. So you can't have it. The potential of the cell must be calculated using the Nernst equation. How do you get numerical values for all this stuff? John. We want to use the Nernst equation. And let's say we put together the cell. You read that on the voltmeter. That 0.05 volts, 0.058 volts. Where does it go in this Nernst equation? It's the E cell. It's the E cell. Because we're talking about non-standard conditions. Notice how they have like 0.08 on. There's some weird funky concentrations on there. They're definitely not 1 molar. So it's a non-standard cell. So this E cell in this case would be the 0.058 volts. Okay. But this is why the Nernst equation is there, so we don't have to set up the whole darn thing to get what E cell is. We're going to calculate it using the Nernst equation. Okay, so this is E cell is what we're finding pretty much every single time. So if that's what we're going to calculate, Jeff, without building the thing, where are we going to get E0 cell? Tables. And why do you know? What's the big hint? The superscript 0. Yeah. You add up those half reactions. Add up those half reactions. How about the, Kathleen, the little n? Moles of what? You're right. When you add up those half reactions, what had better cancel? The electrons. It's really moles. So if 6 electrons cancel, that means little n would be 6. Yeah. It's whatever electrons cancel when you're adding up those half reactions. That's what that little n is. Okay. We're on, Miranda, we're almost there. What about a Q? Q. We even had a name for it. Ooh, which is good. Reaction quotient. Reaction quotient is what we call Q. Does that help? Does that help you say what it is, Pedro? No? Can you remind him, Miranda? What was reaction quotient? It's an expression that's exactly the same as what? The big K. Except it's not at equilibrium is all, right? The concentration's not at equilibrium. So you can't write big K. You have to write Q. That's what the reaction quotient was. So it's just products over reactants. In what reaction? It has to be a reaction. In what reaction? Yeah, whatever this overall cell reaction is. Products over reactants. All right? Okay. So they're sitting there. You have that nice picture. Eric, you spent all this time setting it up, right? Is he at equilibrium? In fact, at equilibrium, the measurement on that voltmeter will be what? It's going to be 0. At equilibrium, it's 0. Right? Because batteries die. They're going to reach equilibrium sooner or later. All those reactants get converted to products. You got this dynamic equilibrium going on. Rate of the forward equals the rate of the reverse reaction, however you want to think of equilibrium. Okay. That means we can rewrite that Nernst equation at equilibrium. Well, this dude goes to 0. And let's not write Q anymore. Let's write K. There it is. You might want to fix it a little bit. E0 cell equals 0.0592 all over n log of K. So if they ever want to know an equilibrium constant for any reaction, you can get it using a table of standard reduction potentials. I guess the reaction has to be electrochemical, otherwise forget it isn't going to work. But that's the idea. Okay, so we can get equilibrium constants out of this stuff. Okay. A voltaic cell has an iron rod and 0.3 molar iron 3 chloride. A zinc rod and 0.2 molar zinc sulfate. The half cells are connected by a salt bridge. Write notation describing the cell. Okay. Your Andy, what are they talking about? Write notation describing the cell. Sometimes they'll call it a cell diagram, but I think they're pretty good about sticking to using the word notation. They want you to write something like what? Like this guy. They want you to write something like this. To me, I have trouble writing this until I identify what those darn half reactions are and things. I have a lot easier time writing this if I identify the half reactions. Otherwise, I don't even really know what's getting oxidized, what's getting reduced, the whole gambit. So it might be a little more work, but let's help poor Smith out, and let's write the half reactions. What would be one of them? Miriam, what do you think would be one of those half reactions? Fe 3 plus. Plus 2. Well, hang on though. I don't know if it could be Fe plus 2 because where's our rod? Iron rod. That's the hint. So it has to be Fe solid. If they would have said an Fe2 solution, I would agree with you. But I think they said solid. They said iron rod, so I'd say solid. The electrons go. Yeah. Now what you could do, you could just search through this guy for him too, right? He's got to be there. Where is he? I can't find him here. We saw him, didn't we? I have a plus 2. I don't have a plus 3 one. Shoot, we're going to need a bigger table. We need a bigger table. Dang, dang, dang. Someone should probably Google this faster than I'm going to be able to find it. Don't we have a big table of standard reduction potentials? Where was that puppy at? Yeah. I don't know where that is. Oh, here's a whole bunch of standard reduction potentials. Starting on page AP20. We're going to have to find them sooner or later, John, so you might as well. And I bet not everything's in that handout. AP20 is where it starts. So you find iron. A, B, C, D, E, H. Iron. Iron, iron, iron. I don't see an iron 3. Maybe it's supposed to say iron 2. I don't even see an iron. Oh, there's iron. Iron 3, but that's going to iron 2. Let's just say it's iron 2 and be, right? Maybe it's a typo. There, life is so much easier. Iron 2, 2 electrons. And we said that is what E0? Iron plus 2 electrons, 0.44 volts. That's when it's forming iron solid. 0.44 volts. Yeah, I think it's positive in the table, isn't it? Oh, there's a negative sign there. Thank you, sir. All right, now we might have to flip it. I'm not saying this is how it's going to be. I'm just trying to identify the half reaction. Okay, now what's the other half reaction? We need zinc solid. Well, let's write it as a reduction. It's easier to find. Right? Zinc solid's over here. Zinc plus 2 is over here. Right? What is it? Zinc plus 2? It does say. The only way you know that it's zinc plus 2 is if you know what sulfate is, which sulfate's a negative 2. So it does tell you. You just have to know what sulfate is. You recognize that? That's a key point. Okay. Now where's that half reaction? Zinc plus 2 and 2 electron, negative 0.76. Okay. So what I did is identify the two half reactions. There they are. Now they both can't be reductions. Where's all my stuff? Nyla, which one do I have to flip one of these or what? Yeah, I have to flip one of them. And the guide is what she said. You want the overall E0 to be positive. Is there a way to do it? If you can't get it positive, you at least get it as positive as possible. Right? No. Flip the largest negative one. Flip the largest negative one. Okay, so that's the one we got to flip. Make him a positive 0.76. So we'll have zinc solid go into zinc plus 2 electrons. Okay. Now, do you see why I couldn't just jump to the cell notation? Because, I can't do all that in my head. Okay. But we can write the cell notation now. I'll give you that part. Casey, how would you write the cell notation now? What would you write first? It'd be the zinc solid, yeah. Then you'd write, yeah, but don't forget to do the line because it's a phase change. And then, did they tell us the concentration of the zinc plus 2? 0.2. So we have to write that, 0.2 molar. And you can write zinc sulfate, but I think it's a lot easier to see if you write zinc plus 2. And then keep going, Amanda. 0.30, big M, iron 2, and then a line. Yeah, there it is. Predict the cell potential. Oh, geez, Nyla, how are we going to do that? We got it? Add those two up? What's that? Yeah, that's what we're asking. Is that right? If you add these two up, what do you get? What's the symbol? E, I know, the algebraic symbol. E cell 0. That's what you get when you add these two up. You get E0 cell. Is that the answer? It's an E, but are we under standard conditions? No, of course, they're never going to say standard. But it's the molarity. You have to look at it and say, oh, shoot, everything's not 1 molar. This is not my answer. What would it be, 0.3 3 or something. You have to use whose equation? Yeah. Do I use this one? No. I would if I was at equilibrium. I have to use the one that we messed up here. Copy that one down. E cell equals, oh, we can put E0 cell in. It's 0.32. 0.32. Isn't it minus? It's minus, right? Minus 0.0592 all, isn't it 0.0592? Yeah, all over n. What's my n? Number of electrons that cancel? 2. Log products over reactants. Okay? Now you pretty much have to add these two half reactions up to see what your overall reaction would be. So you can do products over reactants. Right? Maybe the Fe plus 2 and the zinc gives the iron solid and the zinc. Okay? So I'd have what over what? The concentration of zinc all over the concentration of the iron 2. And the zinc we said was 0.2. And the iron 2 is 0.3. Do we need to square anything? No, because it's just everything's 1 to 1. So we plug everything in, you get an answer. No big deal. Okay. Predict a value for the equilibrium constant. Adriana, what are we going to do? There it is. Yeah. Exactly. I'm not going to give that to you. You have to realize it. This is what I'm giving you. I give you all the equations. It's a concept to jump from there down to here. Okay, that's a concept. So I don't give you this one. But that's it. So E0 cell is, oh, we should put that number in. What is it? Somebody said it was 0.32? Has to equal 0.0592 all over 2 log of big K. Okay. So you can do the math, but how do you get rid of the LOG? Raise it to the 10. So you take the 0.32 times 2, divide it by 0.0592, whatever you get, raise it to the 10 power, and you get your K. Okay. I'll be glad to help you out with the math if you want to practice that. I'm just trying to get through, because some of these are going to get kind of complicated towards the end here. Make sure we get started on them. Calculate the E0, delta G0, and K for the following reaction. Okay. E0. How are you going to get E0? They're already getting kind of sloppy, I think, with their notation, Pavel. I think it would look better if it's at E0 cell, but they didn't do it that way. But how can we get it? Yeah. Identify what the half reactions are. Somehow we have to identify them. Okay? Let's see if we can find them here. Well, we could probably write it out. If we start writing it out, wow, I bet you can just dig them out, right? Is there a cobalt one? Where? I don't see anything. Well, you can just tell me what it is. You see it. I don't see it. Okay, cobalt plus 3 goes to, what did it say? Plus an electron goes to, you guys didn't see it? I thought you guys were saying you saw it. We can find it in here. I think you might have to look in. Cobalt 3 plus an electron. See, we have to go to cobalt 3 going to cobalt 2. Yeah, so it's plus 1 electron, but we need that E0 value, and you have to look in that big appendix. It's 1.92? Okay. And then we need the other one, water's half reaction. I bet you that one we can copy verbatim. Water going to oxygen and H+. That's got to be in there. No, it's not that one. Right? I don't even see oxygen in here. So we're going to have to look in the big table again. Okay. Or you could Google it. Because half reactions have to be given to you. Where is it? It's ozone. Here's water. Water. I see it on page AP 24. Oh, and that's not it. That's not it. Hydrogen, water. That's the one with hydroxide. We need to have a better table for all these guys. John, where is it? Help me out. What do you mean? Okay. You said it's, well, read it as it says in your table. I can't find it. Oh, yeah, but see, we need O2. We need O2.
It's the half O2 gas.
Where do you see it? What page?
It's on AP24.
AP24.
Third one from the bottom, under oxygen.
AP24. Oh, he found it. Page AP24. Way to go, big guy. AP24. I'm going to copy it verbatim. Like, oh, I want the O2 on the other side, though. So I have to flip what they have. Okay. So I'm going to have the H2O over here. Right? And then, I lost it. H2 over here. Third one from the bottom, H2O. A half O2, 2 hydrogen ions, and 2 electrons. Half O2, 2 hydrogen ions, and 2 electrons. Okay. But I flipped it though, right? So it has to be negative 1.229. Okay. If I add these two up as written, right, what do I have to do to get these to cancel? All right. They wanted this. They want 4 COs here. So I'd multiply this one times 4. Right? The bottom one times 2. So if you do that, what do you do to these E0s? Leave them alone. Right. Okay. So but what will my little n be? If you cancel stuff out. Multiplying this one by 4, this one by 2. 4. My little n is going to be 4. That's when you need it. Okay. So, but E0 cell will just be these two guys added up. How do you get delta G0? What was the equation for it? Negative NFE. Right? If it's delta G0, it's E0. If it's just delta G, it's just E. Okay. And then how do you get K? Well, same way we did up here. Right? Okay. So you've got a good handle on this. What I would do is, all right, I just takes a while to find them in here. Okay. When you come by, and I'll be glad to help you out with this. But I can write down the page number. That was AP 24. That's where we got this. Yeah, let's hand out the test.